By measuring the speed of stars throughout the Milky Way galaxy, MIT physicists found that stars further out in the galactic disk are moving slower than expected compared to stars closer to the center of the galaxy. The findings raise a surprising possibility: the Milky Way's gravitational core may be less massive and contain less dark matter than previously thought. The new results are based on the team's analysis of data taken by the Gaia and APOGEE instruments. While Gaia is an orbiting space telescope that tracks the precise location, distance, and movement of more than 1 billion stars throughout the Milky Way galaxy, APOGEE is a ground-based survey. By analyzing Gaia's measurements of more than 33,000 stars, including the most distant stars in the galaxy, physicists determined each star's circular velocity, or how fast the star rotates within the galactic disk given its distance from the galaxy center. Scientists created a rotation curve by plotting each star's speed versus its distance. This curve is a standard graph in astronomy that shows how fast matter is spinning at a given distance from the center of the galaxy. The shape of this curve can give scientists an idea of how much visible and dark matter is distributed throughout a galaxy. What we were really surprised to see was that this curve stayed flat up to a certain distance, and then it started to drop off, says Lena Nesib, a professor of physics at MIT. This means that outer stars are rotating slightly slower than expected, which is a very surprising result. The team translated the new rotation curve into a dark matter distribution that could explain the slowing down of outer stars, and found that the resulting map produced a lighter galactic core than expected. So the center of the Milky Way may be less dense, with less dark matter, than scientists thought. This result creates a tension with other measurements, says Nesib. There's something fishy going on somewhere, and it's really exciting to find where it is so we can have a coherent picture of the Milky Way. The team published their results in the journal Monthly Notices of the Royal Astronomical Society. Co-authors of the study at MIT, including Nesib, are first author Xiaowei O, Anna Christina Eilers, and Anna Frebel. Inside the void, like most galaxies in the universe, the Milky Way spins like water in a vortex, its rotation driven in part by the matter swirling within its disk. In the 1970s, astronomer Vera Rubin was the first to observe that galaxies rotate in ways that cannot be driven solely by visible matter. He and his colleagues measured the stars' circular speeds and found that the resulting rotation curves were surprisingly flat. That is, the speed of stars remained the same throughout a galaxy, rather than decreasing with distance. They concluded that another type of invisible matter must act on distant stars, providing them with additional driving force. Rubin's work on rotation curves was one of the first strong evidence for the existence of dark matter, an invisible, unknown entity predicted to outweigh all stars and other visible matter in the universe. Since then, astronomers have observed similar smooth curves in distant galaxies, further supporting the existence of dark matter. Only recently have astronomers attempted to map the rotation curve of stars in our own galaxy. It turns out that measuring the rotation curve of a galaxy while sitting inside it is more difficult, says O. In 2019, Anna Christina Eilers, a professor of physics at MIT, attempted to map the Milky Way's rotation curve using an earlier set of data released by the Gaia satellite. This data included stars 25 kiloparsecs, or about 81,000 light-years, from the center of the galaxy. Based on these data, Eilers observed that the Milky Way's rotation curve appears flat, albeit with a slight dip, similar to other distant galaxies, and by inference the galaxy likely carries a high density of dark matter in its core. But that view has now changed, as the telescope has released a new set of data, this time including stars as far away as 30 kiloparsecs, about 100,000 light-years from the galaxy's core. At these distances, we are right at the edge of the galaxy where stars are starting to run out, Frebel says. No one had ever investigated how matter moves in this outer galaxy where we are truly in nothingness. Strange tension. Frebel, Nesib, O, and Eilers jumped on Gaia's new data to extend Eilers' initial rotation curve. To refine their analysis, the team complemented Gaia's data with APOGEE, Apache Point Observatory Galactic Evolution Experiment, measurements, which measure extremely detailed properties such as brightness, temperature, and elemental composition of more than 700,000 stars in the Milky Way. By feeding all this information into an algorithm, we try to learn connections that can then give us better estimates of a star's distance, explains O. This way we can go farther distances. The team determined the exact distances of more than 33,000 stars and used these measurements to create a three-dimensional map of stars scattered down to about 30 kiloparsecs across the Milky Way. They then incorporated this map into a circular velocity model to simulate how fast any given star should be moving given the distribution of all other stars in the galaxy. They then plotted each star's speed and distance on a graph to produce an updated rotation curve of the Milky Way. The fact that stars in the outer regions of the Milky Way galaxy rotate more slowly than expected has sparked a new debate in cosmology. This discovery has the potential to reshape our understanding of the structure and evolution of the universe by raising the possibility that there may be less dark matter at the center of our galaxy. Dark matter is a mysterious type of matter that cannot be directly observed, even though it makes up the majority of the matter in the universe. Although its existence is supported by observations such as galaxies rotating faster than expected, what exactly it is still unknown. This new finding in the Milky Way suggests that the distribution of dark matter may be more complex than we thought. Another important implication of this discovery is that we need to re-evaluate models of galaxy formation and evolution. Dark matter plays a key role in how galaxies form and grow. This new finding suggests that some revisions need to be made to these models. So, what will happen after this discovery? Scientists will try to confirm these findings by making more precise measurements and examining different galaxies. They will also develop new theories and experiments to understand the nature of dark matter. Perhaps this discovery will be the beginning of a new revolution in the world of physics. Another interesting aspect of these findings is that they question the role of the supermassive black hole at the center of the Milky Way. The gravitational effect of a black hole can affect the movements of stars. Therefore, the slower rotation of stars could mean that the black hole's mass or rotation rate may be different than expected. Additionally, this discovery may give new impetus to alternative dark matter theories. Popular dark matter candidates such as WIMPs, weakly interacting massive particles, may not be compatible with these new findings. In this case, the search for evidence of the existence of more exotic particles such as axions may accelerate. As a result, the slower-than-expected rotation of stars in the outer regions of the Milky Way could mark the beginning of a new era in cosmology. This discovery could help us answer fundamental questions such as dark matter, galaxy formation, and the structure of the universe. However, we are just at the beginning of this road and many more surprises may await us.